Now that we know what our parent looks like, y equals the square root of x, we can talk about what happens with transformations. And this is going to sound mostly very similar to the last unit, because the transformations are the same no matter when we see them throughout the year. So looking at the screen, y equals a times the square root of b times x minus h plus k. One piece of that is new, but let's focus on the things we know already. The a, the h, and the k. They are the same as they were last unit. So just to remind you the wording that we use for it, the k we call the vertical shift. Any number out here is what you're going to add or subtract if it's negative to the y value. And the a, that coefficient in front, is what we call the vertical stretch. It's what we add or subtract, sorry, not add or subtract, it's what we multiply the y value by. And a quick look at an example. This should look pretty similar to what we've seen before. Not that. Here we go. Here's a function. Notice how the b is not there. We'll talk about that later. But the a and the k do the same thing they always did. So the k, if we move the k, make it bigger, that'll drag the whole graph up. Notice how what's happening to the point that I have marked off there. The parent function, it was 1, 1. If we have a k of 2, that's lifted up to 1, 3. We just raise that y value by 2. If k is negative, we lower it. So now k is negative 3, and so we subtracted 3. Our y value went from 1 to negative 2. We brought it down by 3. If we talk about the a, multiplying, look what happens when we multiply the graph. We know it stretches it out, makes it taller, or steeper is a good word for it. But I want you to focus on the numbering here. Not only does it make it steeper, that's a little bit too vague, but notice how when the a is 3, our y value at this point, which was 1, 1, is now 1, 3. We can compare it to another point on the original function, the parent function. We go through the point 4, 2. On our new function, when x is 4, we can see that the point up there is 6. Notice the connection there again. We tripled the 2 multiplied by 3 becomes the 6. If we would have had a be 2, the 2 doubles to be 4. The 1 doubles to be 2. If the a is 1.5, the 1 is multiplied by 1.5 to get 1.5. That 2, the y value, is multiplied by 1.5 to get 3. So that's how the vertical stretch works. The h we've also seen before. That is the horizontal shift. And that's also adding or subtracting, but this time we do it to the x value. So far, all of this is familiar from what we've seen previously. But then there's the b. This is new. We didn't see this last unit, that b. So I want you to notice first that the b is a coefficient in front of the x, but it's not just in front of the x. It's in front of the whole x minus h. That's going to be important in a few minutes. So make sure you notice that now. And then what we'll do is we'll go back to that Desmos, and we'll take a look at a slide with a b. So notice what happens when I make the b get bigger. It looks a little bit like the same thing when I make the a bigger. Looks like it's getting steeper. But notice that point that I have there, it's not really moving up like the a did. I'll go back to the parent function when b is 1. I'll mark off that point, it's 4, 2. Notice how when I move this over, my point now is 2, 2. I made the b 2, and the y value didn't change. Remember, it was 4, 2. Now it's at 2, 2. Actually, mark off that parent function, 4, 2. Was it 4, 2? Now it's at 2, 2. The y value didn't change. The x value did. It got cut exactly in half. So if the b is 2, the x value got cut in half. If the b was 4, now you can see the x value is 1. The word for what's happening, if you can kind of imagine, I'll go back to the parent function, if you can imagine what's happening here, that orange graph, imagine having your arm or your hand up on the y-axis, between where it says 0 to 5 there, and imagine your other hand on the other side where the plus and minus and the wrench are, and imagine squishing the plus or minus, that hand, all the way down the x-axis, squishing it towards the y-axis. What you're doing is you're squishing that orange graph together. You're compressing it. And that's what that B is called. It is called the horizontal compression. Yes, the graph gets steeper, but that's not really what we're doing. That's sort of a byproduct. What we're really doing is we're smushing the x values together. And as we saw in that problem, it happens with division. We divide the x value. So now we have a fourth transformation to talk about. And so let's look at a couple of examples of making graphs that have those transformations. Look at the first one on the left first. And I will point out before we get started that it is much more important in this unit than in the last unit to use a table of values. With the absolute value, the straight V, it was a little bit easier just to move things left and right and like flip them upside down or stretch the slope. But we don't have a slope anymore. So it's important to use the table of values. So what you're going to want to do is have this parent function pretty well memorized. Luckily, those are perfect squares. They're easy numbers to remember. And what you're going to do is make that table of values every time and then list the changes to x separately from y. You're going to name the transformations, describe the changes that you're going to make, and then make them. All right, this first one, y equals the square root of 2x minus 7. And you know what I'm going to do? So I'm going to call this f of x so I can use that name in my table also. There are only two transformations here. I'll start with the easy one. The k is negative 7, which means we will subtract 7 from the y values. You can imagine the graph. Think of the parent function. Think of the square root graph in your head. And imagine it just being lowered by 7. Well, that's changing the y values, not the x values. That's what the k will do. And then the b is 2, and we said a second ago that that is what we call the horizontal compression. What's going to happen is the graph will be squished in, and that will divide all the x values in half. And so our new table of values for the actual function we're trying to graph here, all of the y values will be just like the old values, only 7 less. So 0 minus 7, 1 minus 7, 2 minus 7, 3 minus 7, 4 minus 7. Notice how nice and orderly they are? If the y values start out nice and orderly, and all I'm doing is adding or subtracting to them, they're still going to be in a nice, simple, easy to identify counting pattern. And for the x values, I'm going to divide them all by 2. 0 divided by 2, 1 divided by 2. I'm going to stick with fractions. For these fractions, go ahead and use decimals if you prefer, but the sooner you get used to fractions, the better, because when we get to more sort of annoying fractions like 1/7 or 3/8, it's a little bit hard to keep using decimals for those. 4 divided by 2, 9 divided by 2, again, call it 4.5 if you want, and 16 divided by 2. And yeah, some of those points are annoying to graph, but you know what? I have enough. I can graph these 3 points, and I'll be able to see my graph just fine. Sometimes you have to graph fractions or decimals, and it's not the end of the world. Notice how I don't really need much in the ways of numbers above the x-axis. I really didn't need anything over here too. So I'm going to graph 0, -7, 2, -5, 8, -3. And even just with those 3 points, you can see the changing rate of change. You can see it's steeper at first and gets flatter afterwards. If you really want to, go ahead, graph the 4.5, -3, sorry, -4. That helps you kind of see the changing pattern. And connect them as best as you can. Just make sure you note which one is the kind of starting point and which one gets the arrow to show it's increasing. Let's describe what we see here with the domain and range. The domain, since we didn't move the x value left or right at all, the x value is still from 0 to infinity. And the range, well, we did drag that y value down, so we started the parent function at the origin at 0, 0, but because we dragged everything down 7, that means the new range is going to start where we dragged it down to, and it still goes up. Okay, we'll do the next one together again. It's a little bit harder because there's a lot more going on. And I also want you to notice in this next example, the order is all messed up a little bit. This 6, it's in the front. It's just still the k. It's the same thing as saying +6 at the end. I don't know why it was put in the front, but don't get thrown off by that. It's still just the k. So we still have, we'll describe our x's and y's separately. It doesn't matter which ones you do first. I'll do the y first, because I have to say something about the x before we do it. So for the y values, we know there's an a. And careful about this one, it's sneaky also. Sometimes you miss it, but there is an a there, it's -1. And the k is 6. So we will multiply the y by -1, which doesn't make it any steeper, but it does flip it upside down. Something we spoke about last unit. Expect to see the graph flipped upside down. And we'll also have to add 6. The x values are a little bit trickier. For the x values, we need to identify the b, which is easy because we're just staring at it. But the h is trickier, and this is a big deal. This is really important because it's easy to miss. You have to factor out the b in order to find the h. I pointed that out to you up above here, where I showed you that the b was factored first, and it was always times x minus h. It always has to look like that. Now, you can identify the b whether or not it's pulled out, but the h has to be separated from the b. So we will talk more about factoring in a couple of weeks. It's a little bit out of order here, but hopefully you remember a little bit from Algebra 1, how to factor out a GCF. So what I'm going to do is rewrite this function. You know, I'm going to give it a name too, so I can give the name in my table. You don't have to. You can call it y if you want, but I'm going to call it g of x. I'm not going to change anything except under that radical, I'm going to pull out that -4 and write it as -4 times x minus 3. What I did was I undistributed that -4. These are two versions of the same thing. -4 times x minus 3 and -4x plus 12. They're the same thing. One has the -4 distributed, one has it undistributed. I need to see the one that's undistributed so that I can recognize that the h is 3. And so we can go back to describing our transformations. The b is -4, so we will divide the x by -4. and then we will add 3. So I'm going to start with the parent function. It's a good habit to label the parent function with the actual equation, like call it the square root of x. Don't just call it y like I did before. This is actually a lot better. 0, 0, 1, 1, 4, 2, 9, 3. Often that's enough. Because I'm dividing by -4 on that x value, I'm going to put 16,4 here because I know that's going to look all pretty when I divide it by 4, so I'll include it. If you don't, usually you'll be fine anyway. And then I will make my transformed function. This is why I gave it the name of g of x, so that at the table it's easier to tell which one is which. And I'm going to follow my roadmap, follow my directions. It's trickier now because I'm doing 2 things to both the y values and the x values. It doesn't matter whether you do x's first or y's first, but it does matter that whichever one you do first, you do the multiplication division first and the adding subtracting second. That does matter. So I'll do the y values first because I wrote them first. I'm going to multiply the y by -1 and then add 6. So multiply 0 by -1 and add 6 is 0 plus 6. Multiply the 1 times -1 and add 6. That's -1 plus 6. Multiply the 2 by -1 and then add 6. That's -2 plus 6. And notice the pattern. Again, because the original y values count nice and evenly, the transformed ones will also. This time, though, I'm counting down because we flipped everything upside down. So -3 plus 6, -4 plus 6, and there's my pattern. Now I'll do the same thing for the x values. This time, though, I'm not going to expect to see a nice pretty pattern here because there's no nice pretty pattern there. But I can still do the math. Divide by -4, then add 3. 0 divided by -4 is 0 still, and then add 3. 1 divided by -4. You have to be either pretty comfortable with fractions, or if you can, convert them to decimals, and you can add, subtract that way. That works fine as long as the decimals stay pretty. Just don't be scared to switch to fractions when we're dealing with with fractions that don't turn into pretty decimals, like sevenths or thirds or eighths or ninths. But hey, a quarter, I can do that. -1/4 plus 3 is 2.75. 4 divided by -4 is -1. This 4. -1 plus 3 is 2. -9/4 plus 3 is 3/4. -4 plus 3, right? 16 divided by -4 is -4. Plus 3 is -1. And I've got enough to make a graph with. Think carefully about where your graph is going to be. My high value up here is this 6 is as high as I get, but notice how my points are all going to be going lower from there. So I don't need anything above 6. And my x values, I go as far to the right as 3. But notice how all my other numbers, they're going backwards, 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 negative. So I don't need anything more than 3 on the right-hand side. And so when I make my line, I'm not going to leave that much space on the right. Okay, and then we'll plot some points. 3, 6. You can skip the 2.755 if you want. It's hard to graph quarters on here. I've got enough points without it. Hopefully we see what I did wrong right now. I said -1. This 4, or that number 3, is definitely not right. I can't have 3, 6 and 3, 4 in the same function. So I'll just quickly look back. I did divided -4. 4 divided by -4 is -1. When I added 3, I don't know why, somehow I wrote down a 3 there, but clearly that's not right. That should be a 2. So my next point is 2, 4, and then -1, 2. And again, you can certainly put the points in the middle in if you want, but you don't have to. This is enough to make my graph. Notice how the arrow is going to be on this side because the graph, the x values, if we were to keep going here, we'd keep going backwards here. And so describing my domain and range this time is going to be the other order as before. Instead of going from 0 to infinity, now I'm actually only going up until the x value here is 3. So it's from negative infinity to 3 is the domain. And the y values get up as high as 6, so it's from negative infinity. And let me just correct this real quickly. That should be a parenthesis. From negative infinity to 6. And so hopefully you're now in good shape for graphing a square root function, even if it has some complicated transformations.